We study X14Q rigid body dynamics. A bead of mass m at point P is constrained to move around the circle of radius r without friction in a vertical plane under the constant gravitational acceleration. Discuss the rotational motion of the particle. The position vector is er hat, that is a unit radial vector, and the unit tangential vector is written like that. The rotational inertia of the particle about the z-axis. First of all, the axis of rotation is about the z-axis. That is not shown here. It is coming out of the page. And z-axis, okay, that z-axis, or E3 hat, is the axis of rotation. And perpendicular distance from that axis of rotation to the particle is x per vector, lever arm vector, and x per vector has the magnitude is always r. And rotational inertia is x per vector squared mass, and this is r squared, and point-like mass, this is m. So mr squared is the rotational inertia of this particle. The orbital angular momentum of the bead we have to compute the position. Position is x vector r e r hat, and momentum. Before we compute the momentum, x dot, that is r theta dot e theta. Unit tangential direction is e theta hat. Mass multiplied by this velocity is the linear momentum, and x cross p is product of this mr squared theta dot er e theta. This is e3 mr squared theta dot e3 hat. Here mr squared is moment of inertia, so I have replaced with I. Kinetic energy of the particle. Kinetic energy of the particle is a velocity of 1/2 m velocity squared. So this is 1/2 m r theta dot e theta squared. So what we have is 1/2 mr squared theta dot squared. So this is I. 1/2 I theta dot squared. I is mr squared. At angle theta, the potential energy of the particle, okay, it's easy to define. The height of the particle relative to the horizontal axis, x-axis. So this is height. So height is r sine theta. Potential energy can be chosen as mgh, so mgr sine theta. However, we can always add the arbitrary constant in here. So this is the most general form of the potential energy of the particle due to the gravitational force. Because the gravitational force is conservative, the total mechanical energy, that is the sum of the kinetic energy and potential energy, is conserved. conserved means its time derivative is 0. If we take the first order time derivative of the total mechanical energy, we just copy the kinetic energy here, copy the potential energy here, and this is a constant, arbitrary constant. We take the time derivative of the kinetic energy, and kinetic energy has the theta dot squared, and what I need to do is making use of chain rule. Okay, so what's that? 2 theta dot. What's that? Theta double dot. Therefore, chain rule gives the time derivative of the kinetic energy is 1/2 this factor of 2 cancels, mass r squared, theta dot, and theta double dot. Next, we take the time derivative of this. R is a constant, so we take the derivative of sine with respect to angle, and then time derivative of this angle. This is a theta dot, and this one is a cosine. Now we find that theta dot appears twice. We factor this theta dot out. Then theta dot is here, the factorized one. To be this equation to be true for any theta dot, we remember theta dot decreases as it rises up, increases as it goes down. Therefore, at some point theta dot could be 0 at something like a turning point, but in general theta dot does not have to be 0. So in that case, I cancel this to find that this is always a 0. This is nothing but the equation of motion. I divide mr squared both the sides to find that we have a double time derivative of the angle and g over r cosine theta. By the way, this is the angle theta measured from the x-axis. We could have measured the angle from this direction. This is usually measured for the pendulum. In that case, the angle measured from the negative y-axis, this should be the angle theta prime, and this is additional angle 1/2 pi. Okay? Wait a second. Theta angle theta prime from measured from here. Okay. Raise this angle from here, theta prime, and this is right angle. So we have the identity theta plus 1/2 pi is theta prime, or theta equals theta prime minus 1/2 pi. Okay, we have cosine theta. This is theta prime 1/2 pi. Cosine theta, or cosine theta prime minus 1/2 pi. We know cosine an even function. I can replace with 1/2 pi minus theta prime, and there is an identity. This is a sine theta prime. Therefore, this equation of motion can be written in the form like that, replacing cosine with sine when the angle is measured from the negative y-axis. Okay, in that case, the angle measured from here. So pendulum, just like usually of writing the pendulum equation. So who knew? You can derive this equation of motion. Usually it is rather difficult for you to derive the equation of motion directly from Newton's laws of motion for the rotation version. However, what we have done is nothing but the conservation of energy. This is the merit of using scalar. For example, the Euler and Lagrange derived a new way of writing Newton's laws of motion using Lagrangian mechanics. Lagrangian mechanics is involving the scalar that involves kinetic energy and potential energy. In addition, the Hamilton derived a method with the Hamiltonian, and the Hamiltonian is nothing but the total mechanical energy what we have derived. But fortunately, treating the energy rather than the force directly is much easier to deal or to compute. But unfortunately, from high school until the university, they don't teach you how to make use of energy. When you learn total mechanical energy conservation, you are asked to find out a very simple thing, just like speed, that high school students can do. But I'm very sorry about that. Why you do not make use of this very simple way of making use of the total mechanical energy? Too unfortunate if you don't study this. Okay, anyway, this is nothing but the net force equation. This net force comes from the gravitational force, and that net force comes from the normal force. All of the contribution has been merged into a very simple energy conservation equation. If you wanted to derive this equation with this kind of way, it could have been very, very complicated, and usually most of you make sign mistake. Okay. And this equation of motion linear version is actually the same as the rotational version. Next, we consider the pendulum equation just we have derived. And actually, the pendulum equation was first derived by Christian Huygens. And you know, the pendulum has been studied for the first time very seriously by Galileo Galilei. And he understood the independence of the period regardless of the large amplitude. So that comes from this fact, but that is not exact. Instead, Huygens found this exact equation, and he has derived the period formula 2 pi square root length of the pendulum divided by the gravitational acceleration. Okay, that comes directly from this. If we make an approximation in the limit as the theta goes to very small, but actually the actual angle of rotation, it varies from 0 to pi, here, there, and pi is nothing but 3. It does not go very far. So this 3 is not a very seriously large number. That's the reason why the amplitude is almost independent. Does not change the period of the pendulum effectively. Anyway, we started the expansion formula of the sine theta and cosine theta, and in the limit, as the theta goes to a very small number, this oscillating series can be approximated as a linear function. And in the case of cosine, as theta goes to 0, it approaches 1, and the correction is a quadratic term, proportional to theta squared in the negative sense. Anyway, if I substitute this one into this equation of motion, what I can do is I find gravitational acceleration and length of a pendulum, both of them are positive number. If they are positive number, I can express this one as omega 0 is the square root of g over L, then g over L is omega 0 squared. So I replace this one with this. So simple equation. This is called the equation for the simple harmonic oscillator. Simple harmonic oscillator. The reason is that any trigonometric function such as a sinusoidal function, sine or cosine, we say this is a harmonic function. So solution of this pendulum is sinusoidal, and using this periodicity, Huygens constructed the watch, the clock. Omega 0 is called angular frequency, and that is the square root of g over L. Period is 2 pi over omega 0, and the solution of this equation of motion is actually the linear combination of sine and cosine. Let's see, if I substitute t equals to 0, I find 0. That's fine. If I take the derivative, this one, omega 0 sine omega 0 t, and next term plus omega 0 cancels the denominator. I substitute 0, so theta dot 0 is theta dot 0, and this one disappears, plus 0. Okay, so it is perfect. If my solution satisfies the theta dot 0 and theta dot 0 and theta dot 0, because of this constraint, theta n plus the 2 derivative at 0 is completely determined by theta and that derivative. And if you go smaller and smaller, then you can always determine any derivative, any order of derivative at time equals 0 from this relation. So the only parameter you require to solve this equation of motion are these two. And this one gives a very strong constraint that the coefficients of the Taylor series expansion that we have derived is just determines all of the coefficients of the higher order derivatives. If I sum everything all, that infinite series of constructs, the even function and odd function, they are cosine and sine. Okay, next, a uniform disk of radius r, mass m. Okay, this disk, we have a rotational inertia of a disk. It has been derived in X14. And remember, you should be able to 13 and 14 should be able to evaluate the moment of inertia of various objects, and you can refer to the detailed computation of integration. Due to the tension T of an unstretchable string attached to a block of mass m, moving vertically without friction. I is the rotational inertia of the disk about the z-axis. Discuss the motion of the system. We like to make use of the total mechanical energy conservation frequently. So why don't we study the kinetic energy of the system? We have a constraint of the system. The distance of travel by this block is straight, and if I assume it is x, because the string is not stretchable, the arc lengths are theta of the rotation is completely determined by the translational distance traveled by this block. Therefore, x equals r theta, and x dot is clearly r theta dot. It's a very strong constraint. I'd like to know what the kinetic energy is if I treat everything altogether as a rotational motion. Yes, it is rotating like that. We have this disk whose rotational inertia is 1/2 mr squared. Uniform disk has 1/2 mr squared. And then we have 1/2 small m x dot squared. If I substitute this relation in here, it is nothing but 1/2 mr squared theta dot squared. So this one is actually the rotational inertia about this z-axis, this perpendicular distance from this axis of rotation to the travel of this block is nothing but the radius. That's the reason why I have additional rotational inertia added up to the previous rotational inertia due to this pulley, uniform disk pulley. Anyway, and then I have finished computing the kinetic energy of the system, and then I need to consider the potential energy. Even though it is rotating arbitrarily, because the center of mass of this pulley doesn't change at all, the only potential energy change comes from the translational motion vertically. Therefore, the potential energy can be treated. This is the height from the bottom. Then this x is related to the height by negative sign, neglecting the arbitrary constant p's. Therefore, the potential energy of the whole system is the potential energy of this block, and that is expressed as a negative of mgx. Now we again substitute this identity. X is r theta. So we completed the expression for the total mechanical energy. That is completely expressed in terms of theta and theta dot. That's it. After we obtain the solution for this equation of motion for theta dot, then I can determine x dot by multiplying radius r. Okay, we are all set. Now we are happy to apply the conservation of the total mechanical energy. That's fine. How? I take the time derivative of this, and E dot equals always 0. Therefore, now we can take the derivative of this by applying what? Chain rule. Chain rule gives, again, theta dot squared time derivative. What's that? Theta dot derivative of theta dot squared and time derivative of theta dot. What's that? Theta double dot and 2 times the theta dot. In such a manner, this one, after taking the time derivative, it brings a factor of 2. To cancel the 2 in the denominator, we have a mr squared, this factor, and we have a theta dot factored out altogether. Here, if I take the time derivative, everything else is constant except that we have a theta dot. So we have a deleted theta dot because the theta dot in general, for any time, at some point it could be 0, for example, in the initial condition, but in general, arbitrary case, theta dot can be cancelled. As a result, we can determine the theta dot, the step theta double dot, and that determines x double dot because theta x dot equals r theta dot and x double dot equals r theta double dot. Okay, and then if you make use of the equation of motion, until now we didn't make use of any relation regarding the tension. Now we specify the tension and write down the equation of motion for a single block by making use of tension that is applied along the direction above. Then we can solve the equation. Just like before, we can take the limit as a capital M goes to infinity relative to small mass, or small mass is going to infinity relative to the capital M to find the special relationship. Okay, so this is a way to apply the total mechanical energy conservation to solve the very complicated problem involving rotation of rigid body. That's it for today. Thank you.